So I would like to more stress on the pulse transient method, which was used for measuring the thermal properties of rocks, and the application why there is a need to study the thermal properties of rock, because if we know the heat parameters and transfer parameters of the rocks, we can use it for storing heat inside the earth bedrock. For example, if you see this picture, so here are some hot needles which are penetrated inside in below the house, and there can be installed a heat storage system. And if we know the proper thermal parameters of this heat storage system, it is possible for us to understand how the heat will dissipate in or out from the system, how well it can be stored, and for how long it can be stored. So for that purpose, it is very important to know the thermal properties of the building material, for example, rocks, wood, concrete, soil, grass, everything. So in this my work, I will be just focusing on thermal properties of rocks. So as I was trying a lot to find some information about pulse transient technique, it was I feel like maybe it was not available, so I thought to make a presentation on it. So pulse transient method is basically a transient, belongs to the transient technique. Transient for by what it means, something like moving, dynamic, changes with the time. So the main principle of this method is that you will have samples, maybe two or three, and if you see here, they're like cylindrical samples, two or three samples, and there will be a heat source. And in this transient methods, the heat is passed through this heat source, and depending on the nature of the material, the heat will penetrate inside the sample. And the third sample and the second sample, there will be a thermal sensor, for example thermocouple, which will be responsible to measure the thermal response of the thermal response to this thermocouple. So this is how this pulse transient method works, and it is very interesting to see if we lose some heat from the sample. Then if we have good contacts in between the samples, if whole chamber is kept in an good room temperature condition, for example good pressure, good humid, good temperature, not like in hot summers. For example, if you put your samples in the inside the chamber for, let's say, at 45 degrees Celsius like in India, and then in the midnight, in you will feel maybe 23, so it will be like 20-degree delta T. This is like quite too much. So it's rather recommended to do experiments in the night because of the low change in the temperature, to get something relevant value. So in this graph, we are missing the axis title, but I can explain it. So this increasing thermal response, it is the graph, and this graph is plotted with the time, and these arrows are telling that the temperature here, it's sometimes for rocks and wood it is go maximum to 0.5, in between 0.5 to 1. And the maximum height of this temperature response, it's very important for us, because this will let us know the maximum of the temperature response, Tm and small tm, at what time, and through that we can calculate and derive the formula for the maximum, which is called as 1 point evaluation procedure. In this pulse transient method, we have like more than 9 or 15 models, and in this presentation I'll be showing two models only. One, this is called cuboid, and another is called slab model. So from experiment, it is possible to get these three parameters, basic parameters: thermal diffusivity, specific heat, and thermal conductivity. But if we have some another models, So we can find heat transfer coefficient in between specimen and surroundings, that is cuboid model, and heat transfer coefficient between specimen and heat source, and heat capacity of the heat source also depend on which model you want to use. So this is very interesting to know, like how pulse transient technique works, and what all parameters you can get, because it is very special and very unique in our case, because usually we'll find thermal diffusivity, thermal conductivity in specific heat only, not other specific parameters. But we have model that helps to understand these another thermal transport parameters. Let's go to the next slide. So here we have transient tester RTB101. These pictures I've taken from my supervisor's article and his colleagues' presentation and papers in my thesis, and I have referenced it also. So this picture is actually showing the components that are used for the experiment. Now, after performing the experiments, we have some models, as I said. So, for example, when it is ideal model, then it means that specimen and geometry is infinitely large, and the heat source is infinitely thin with negligible mass. So thermal properties will also be like kind to be very ideal. We have to find out how. Then the contact is very ideal, no influence. Thermocouple is very good, infinitely very small, negligible mass. So in ideal condition, as we know, we do not consider so much of boundary conditions and parameters. But there could be a problem, because in real world we know this contact cannot be ideal or not homogeneous, because if there are some cracks or some wood or concrete, their nature, their physical texture is different, so it cannot get the ideal contact. And also there has to have a heat loss, because if the contact is not ideal, of course there will be heat losses from the sample surface. So basically I will show in this presentation how this methodology of slab model is very good, because it will help us to calculate and to know the heat capacity of the heat source, and contact heat resistance by introducing the heat transfer coefficient in between heat source and the specimen body. So the motivation of this study was to just understand how this two parameters work in the slab model, and how we can play with these two parameters to understand other three thermal properties like thermal conductivity, diffusivity, and specific heat. So this is the formula. I have just taken the direct equations and some definitions, and in the last you will see that there is a temperature response formula, which is a subtraction of two stepwise responses, which is shifted in the time equal to the duration of heat pulse. So in the simple terms we can understand in this way, that when we give a heat pulse to the inside the chamber, it is better to stabilize the experiment at least for 8 hours or maximum 8 hours, because there is a high probability that these experiment and in this experiment there can be some thermal history present inside it. So to avoid that, we need to stabilize it, and this means this stepwise it is a subtracting, because when we give the heat pulse, then during the calculation it is already shifted. I'm sorry. So it is already shifted. Therefore, we need to subtract it from the initial T naught to get it at the basic level. This is uncertainty analysis and parameter estimation. This is nothing but how the error and how the theoretical error propagate in the experiment, and how we can understand that the small sensitive coefficient value can bring large uncertainty in the experiments. So this is how our results look like, and this arrow is the time window interval, what window we are selecting to get the thermal property, and here is the alpha. So here in this picture you will see The difference between the maxima and the minima is so less that it looks like this is very very coinciding with the experimental values, and the error is so low. And yeah, you can see that this window interval of the slab model estimation of heat transfer coefficient values for fitting with all free parameters are out of given scale because of high uncertainty. Yes, this means this red line there were when the all parameters were free, the scattering was beyond the scale, and which we cannot measure, we cannot show it in the paper. So we we made analysis and some trick how to converge this scattering in like some line, or you see that when we put some constants, we got the difference is like so low, less than 1%. And that's how we can rely on these values to publish for heat transfer coefficients. So in the next presentation, I'll be explaining what was the trick that we use and how we performed and how we got these